Hi. So we're now moving on to Newton's laws of motions. Actually, the last lesson I did Newton's third law. So continuation. We're going to be able to describe Newton's laws of motion and use them to describe the motion of objects. Mostly focusing on first is Newton's first and second law. But let's start off with just reviewing some important things that we're going to need for this. What are the units for mass? The units for force, the units for acceleration, and the units for speed. Then can you state Newton's third law? And then can you draw a free body force diagram for a mug on a table? Go. Have you done that? So let's try the answers. The units for mass are kilograms. The units of force are newtons. The units of acceleration are meters per second squared. And speed are meters per second. Newton's third law: if object A exerts a force on object B, object B exerts an equal and opposite force on A. Draw a free body diagram for a mug on a table. Well, I'm not going to draw the mug, I'm just going to draw it. Why not? Let's draw the mug. There is my mug. And then remember what you're supposed to do. You're supposed to do the non-contact forces. So you've got the weight of the mug, or the pull of the earth on the mug, and then we've also got the pull of the mug on the earth. And then you've got the table, mug on the table, and then you've got the mug pushing into the earth, into the table, mug, push, table, and then table, push, mug. And so if we're going to draw the thing, we're just going to draw the ones involving the mug, and so we just have weight and the table pushing on the mug. That's a bit cluttered. Soz. Okay. Sorry, cat just fell downstairs. Okay, so what are balance forces? We're going to look at what happens when the resultant forces. Remember, resultant forces are after you've done. In the last lesson, we did an equation where we had like an arrow pointing one way with 30 newtons and an arrow pointing the other way with 50. And we noted the resultant force was 20 newtons. That's the resultant force. So there are lots of different forces acting. But once you've done the maths and worked out what's the final forces, that's the resultant force. And we're looking at what happens if the resultant forces are zero. If the resultant forces are zero, there are different scenarios to look at the resultant forces. Here we have an old man cycling on his bicycle. Let's look at the forces involved. We've got the weight going down, the reaction force of the road pushing back, that's going up. We've got the air resistance pushing back and friction due to cycling and movement pushing back, and we've got thrust pushing forward. If we were to draw all of these forces tip to tail, we'd end up getting zero forces. But look what's happening to that man. Is he moving? Yes. The forces are balanced, but he's still moving. He's got no net force on him, so he doesn't change. He keeps doing what he's doing. He keeps going in the same direction. Let's look at the next one. Here we have a skydiver. His weight is pulling him down. The air resistance of the air inside the parachute is pushing up. They're the same. He's still moving. Those forces are balanced, but he's moving at a nice, steady, terminal velocity, slow speed. Have a skier skiing downhill. The weight and the reaction are the same, and the thrust, the air resistance, and the friction equal and opposite. If you have balanced forces, you can still move. If you have no net force, you can still move. The only thing that happens with no net forces is if the forces on an object are balanced, if there's no net forces, it won't change. So if it's not moving, it will carry on not moving. But if it is moving, it will keep moving at the speed and the same direction that it was moving before. If you have zero net forces, that means you have zero change. If you're not moving and there's no net forces, you have no movement. If you are moving and there are no net forces, then you carry on moving. Some people find that kind of tricky to understand. How can something be moving if there's no forces? It's more of a case of you need a force to cause something to change. So if you are moving, then you wouldn't just expect you to stop suddenly. You will only stop if something happens to you. Now, normally that's, well, so how? Pause, take that note down because it's important, and then we'll look at the next situation. Check. Right. So, yeah. I'm going to jump to 2 seconds. Normally, what happens is there's friction. So when you are cycling along on your bike, not cycling, you don't cycle with your hands. When you're cycling on your bike, you're pushing forward, you're pedaling, so you're pushing forward. So that's like a thrust going forward. So you're putting a constant force. So you would think you would constantly get faster and faster and faster. In reality, there's friction and air resistance. So that slows you down. So sometimes what happens is when you think you're trying to make an unbalanced force to move things forward, there are other forces that come into play that try and slow it down, that counteract. Friction always slows things down. Friction always goes in the opposite direction of thrust. So sometimes, even though you think the forces might be unbalanced, friction or air resistance comes along just to ruin your day. I'm going to go back to the questions. Can you explain some questions? Can you explain, write down and explain the resultant force of an ice skater moving at a steady speed? Maybe draw it as a little dot. Can you draw a free body diagram of you traveling in a car? You traveling in a car at a straight line at a steady speed. Explain in terms of Newton's third law why a stationary pen on your desk is in equilibrium, but a full pen that falls on that desk is not. If you put a toy car on a ramp, then you raise the ramp so the car travels at a steady speed. Suggest why this slope is called friction compensated slope. Ooh, tricky. We'll do the answers another lesson. Don't pause, answer the questions. Oh, wait. Done? Splendid. Right, we've done this one. Okay, so here we have a situation. What happens when the forces are unbalanced? Let's look at what happens when the forces are unbalanced. So we have a hot air balloon. Let's show when the forces are unbalanced. You turn on the burner, the upthrust increases. So therefore, they come back into line. So right now the forces are balanced. This balloon doesn't drop to the ground, it's in the air, so it stays in the air. If we turn on the burner, the upthrust then increases, meaning the object starts to speed up, going up. It goes up faster than it was before, so it's changing direction. So it wasn't moving, so it starts moving. Forces are unbalanced, it goes from not moving to starting moving. Here we have old lady in a car, dog. Something's gone wrong with the dog. Nothing's happening. The forces are at the moment balanced. What happens if we unbalance? Let's take the handbrake off. Oh dear, look at the dog. Sheer terror. If it's unbalanced forces, if there's not enough, because the weight, where's the arrow gone? If the weight going down and the friction, and these things are not balanced, then you start to move and you start to speed. Doesn't appear to be aware of anything that's happening. Terrifying. And here we have an individual traveling on his moped with terrible posture. All the forces are constant. Let's change. Can I change this? Oh, press the brake. As I press the brake, the thrust slows down. Reduces, sorry. The thrust doesn't slow down because it's not speed. The thrust reduces. And so therefore, he slows down. Here, he takes the brake off, so the thrust gets bigger. Means he starts to speed up. So, if the forces are not zero, then we say they're unbalanced. If the forces are not zero, we say they're unbalanced. And if they're unbalanced, two things can happen. They can either change their speed or change their direction. I suppose you could also say a third thing. It could change its shape, but changing its speed. So if its speed is zero, it can start moving. If its speed is high, the unbalanced forces could cause it to slow down. Changing its speed is a consequence of having unbalanced forces, but it could change its direction. It could be traveling along, and then a nudge on the side causes it to change the direction to go suddenly sideways, like a bird flying in through the air, and then all of a sudden a gust of wind comes along from the west, causing the bird to start veering off in a different direction. So if the forces are unbalanced, two things occur, or can occur. You either change direction, or you change your speed. Another thing to note down. Pause, write it down. In summary, no force, no change. That's the easiest way to remember it. If there is no force acting on something, whatever's happening will carry on happening. It would be weird if things just suddenly started happening when no forces were occurring. So if someone's moving, they will carry on moving. If someone's not moving, they will stay not moving. No force, no change. If there is a force, well, then you will get a change. It will speed up, it will slow down, it will change position, maybe change shape. No force, no change. There is a force, there is a change. If there is a change, if there is a force, then we can use this equation. Force is equal to mass times acceleration. F equals ma. And we can use this to work out how much change there is going to be. So if we know the resultant force, and we know the mass of an object, which is how many particles it's made from. What's mass measured in? Kilograms. Excellent. So we know the mass of an object, and we know its force. We can then work out its acceleration. If it has a positive acceleration, it's going to start speeding up. If it has a negative acceleration, it's going to start slowing down. So we can use this. Newton's second law basically says if there is a force, you'll end up with an acceleration. Obviously, force is measured in newtons, mass in kilograms, and acceleration in meters per second. So let's have an example. Pen working, please work. Oh yeah. So we have an aeroplane of mass m equals 1,400 kilograms. The plane accelerates. It produces here's my plane. Quality drawing. It thrust of 4,000 newtons that way. It has friction opposing it. 300 newtons. So what's the net force? The net force is 4,000 minus 300, which is equal to 3,700 newtons. But what's the acceleration? Well, the equation is F equals ma. So F over m equals a 3,700 divided by 1400. Can't do that in my head, so I have to put my calculator. 3,700 divided by 1400 equals 2.64 meters per second squared. Pretty simple. Pretty simple? Simple. Time for you to practice. Here we have some questions. Just use the equation. Should I put it into a triangle for you? F, M, A. A trolley of mass 15 kilos is accelerated at 3 meters per second. What force is needed to do this acceleration? A force of 20 newtons is used to accelerate 250 grams mass. Careful, grams is not kilograms. Convert. What is this acceleration? A boat accelerates at 1.5 meters per second. whilst pulling a skier who has a mass of 68 kilos. What is the resultant force on the water skier whilst the boat is accelerating? Must the force from the boat pulling the water skier be less than, the same as, or greater than the force you calculated in part C? Explain your answers to part D. And another water skier of half the mass of the skier in part C experiences the same acceleration. What is the force? So, pause and answer those questions. Is that it? That is it. Check it out. Easy for you today. How nice. So, have a go. Have a go. It's worth noting in these ones. So, remember, when there's an acceleration, you're increasing speed, you notice it. So, next time you're in a car and you're going at a constant speed, you don't really feel the car, like you can feel it moving because it's bumping, but you don't feel yourself being pushed back. But if you've got a dangerous driver as a parent or a car with a high acceleration, when the car's accelerating, when its speed is increasing, they slam the accelerator down, you feel yourself being pushed back, you feel the force. But when the car's going at a steady speed, you all move together. You don't feel that force. So the forces are balanced, steady speed. Forces are unbalanced, change. Answer the questions. I'll give you the answers in the next lesson. You're doing really well. Good luck. Love you. Bye.